Hello students, this is Mr. Wilsey, and in this video we are going to be studying a topic called vectors. So I want you to get out paper now, and I want you to jot down some notes with me as we go through this video. Now, a vector is a quantity that has a size and a direction. Okay? And a slightly fancier word that we sometimes use for size is magnitude. Okay? Now, you've already seen plenty of examples of vectors. Okay? Because we can represent vectors by an arrow. Okay? So, vectors, or vector quantities, can be represented by arrows, because the arrows have a certain length, which represents their size, and of course the arrow points in a certain direction. Okay? Now, we have already studied at least two different types of vector quantities. So examples of vectors that we've studied so far include velocity. Velocity is a vector. And then another example of a vector that you've seen before is a force. Let me show you an example of velocity as a vector in action. Okay? So I have a Java applet here, which shows a little red ball that is moving from side to side. Now the green arrow, when it appears, represents the velocity of that ball. You can see that the arrow's direction indicates the direction of the ball's motion, and the size of the green arrow indicates how fast the ball is going. Okay? The ball's speed. And so we've kind of glossed over this point a little bit, but speed is the magnitude of the velocity vector. Now we can experiment around with some different types of motion that this red ball can undergo. For example, it can go in a circle, like this. Now in this case, the ball has a constant speed because the size of the arrow does not change, but the direction of the arrow is constantly changing. That means that the velocity is constantly changing. Now, you might be surprised, but another example of a vector quantity that we have studied is acceleration. Acceleration is also considered a vector. Now, we haven't really talked about it as a vector, but let's do that now, okay? So let's just imagine that we have an object, and it has a velocity vector that looks like that at some point in time, okay? So let's say the time is 0 seconds at this point, and this object that we're talking about has a velocity of an initial velocity of, let's say, 10 meters per second. Okay? Now, at some later point in time, let's say, I don't know, 5 seconds. So 5 seconds have passed, and the object now has a final velocity of 20 meters per second. Now this means that we're going to have to add some length to the initial velocity vector. There we go. So the velocity increases by a certain amount. Okay? So we're going to say that the change in velocity equals 10 meters per second. Okay? I'm going to put a little plus sign in front of there to indicate that the change in velocity was positive. Okay? The object that we're talking about, and if you'd like, it can be a little red ball, just like in the movie that we just watched. Okay, it's a little red ball. Its velocity increased by 10 meters per second. So the final velocity vector is going to be the initial velocity plus the change in velocity. So the final velocity vector is going to be about that long. Okay? It's no longer fitting on my screen. There we go. There we go. Now I'm just going to take this down here. Okay? Change in velocity. So we have two different snapshots of this red ball at two different points in time. Okay? And the change between the two situations, the two snapshots, is this increase in velocity. Now, I hope that you remember that acceleration is a change in velocity. But it's more than just a change in velocity. It's a change in velocity over a certain time interval. Okay? So it's a change in velocity over a change in time, basically. Change in time. Now the way that we wrote this formula is that acceleration is equal to a change in velocity over a change in time. Okay? Now, because change in velocity can also be represented by a vector, just like velocity can, that means that acceleration can also be represented by a vector, by an arrow. And in fact, the acceleration vector points in the same direction as the change in velocity vector. Now, we can't quite say that the acceleration vector is the same thing as this change in velocity vector because the acceleration vector is divided by the change in time. Okay? So for instance, if we come back up here, the change in velocity is positive 10. Okay? So let's go ahead and write that down. Positive 10 meters per second. But it takes 5 seconds to go from 10 to 20. Okay? So that means that we're going to have to take the 10 and divide it by 5 in order to get an acceleration of 2 meters per second. Each second, the velocity of the ball increases by 2 meters per second. Now, let's take a look at the other type of vector quantity that we have studied so far, forces. Okay, so I'm going to bring up an answer key that should look familiar to you, if I can find it. There it is. So here is the, yes, thank you, iMovie. Here is the answer key to the drawing force diagrams worksheet that we worked on a little bit ago. Okay, so I'm just going to take a screenshot of this situation here. So we have a book at rest on a tabletop, and the force diagram looks like that. I'm just going to replicate that force diagram real quick. The size of the support force relative to the size of the weight tells you that they cancel each other out. They cancel each other out. At least they should. There we go. Now, because the two forces cancel each other out, that means that the forces acting on this book are balanced. Now, let's bring back something else that we talked about in class. If the forces acting on an object are balanced, do you remember what Newton's first law of motion says? If the forces acting on an object are balanced, that means that an object that starts at rest will stay at rest. Okay? So this book is not going anywhere. Now let's take a look at another example of a force diagram from that same, where is it? From that same answer key here. Okay, so a child pulls on a rope to drag a sled rightward at a constant speed across the snow. Consider frictional forces, but neglect air resistance. Now in this case, the forces are balanced again, okay? And I'm sorry, but I just got finished watching the video that I've made so far, and I realized that I say okay quite a lot. So I'm going to try to consciously not do that so much, because I can understand how it might get rather annoying after you hear me say okay and now as often as I do. So, although to be honest with you, it's probably just going to stand out much more as I say it in the future. But I will do my best to not do it. Anyway, so here is our sled. And we have 4 forces acting on the sled. The support force pointing upward balances out the weight, which points downward, and the force of kinetic friction, pointing to the left, balances out the force that you apply. The force that the child is applying in the sled by pulling on it. Actually, now that I think about it, this should really be tension instead of applied force, because I explicitly said that the child is pulling on a rope, but that's not a huge deal. We won't split hairs about it. Now again, just like in this example, the forces are balanced, but in the last example, the book wasn't moving. In this case, the sled is moving. What I drew here in the black was, I hope you will recognize now, a velocity vector. My movie is jumping again. The movie gets happy. So this black arrow was the velocity vector. Notice that I drew it completely separate from all of the arrows over here. A force diagram just has vectors representing the forces acting on that object. So this is the force diagram up here of our sled. But down here, we can say that this is a velocity diagram. I'm actually just making that up. But it seems to work, okay? The point is that you don't want to mix all of these different types of vectors together. Okay, you want to keep your forces in one diagram and your velocity in a separate diagram. Now here's something else that I hope that you notice at this point in time, after we've gotten a chance to study some more physics since the last time you saw this. This sled is moving at a constant speed, and you can also assume that it's also traveling in a straight line, not going in circles or anything. So if the sled is going at a constant speed, and it's traveling in a straight line, and of course a straight line means that it's traveling in a constant direction, I hope that at this point in time you realize that this implies that the object has a constant velocity vector, because the size of the velocity is not changing, otherwise it would be a non-constant speed, and the direction is not changing, otherwise it would not be going in a straight line. So this sled has a constant velocity. The book also had a constant velocity. Its constant velocity was 0. It wasn't going anywhere. So in both of these cases, we notice that when the forces acting on the object, and this is so important that I'm actually going to write it out for you. When the forces acting on an object are balanced, the object has a constant velocity. This is a very profound statement, and in fact, this is a succinct way to state Newton's first law of motion. Here is the way that we saw Newton's first law of motion originally. The way that we originally thought of Newton's first law of motion was that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed in the same direction unless an unbalanced force acts on the object. And we've just rephrased it a little bit to use this word velocity now. So when the forces acting on an object are balanced, the object has a constant velocity. But what if the forces acting on an object are not balanced? That is a curious question. And this question leads us to, drumroll please, Newton's second law of motion. Newton's second law of motion answers the question: if an object experiences an unbalanced force, then its velocity will change. This means that it could speed up, it could slow down, or it could change direction, or it could do all three. Now I want to change this slightly. Instead of an unbalanced force, I'm going to use a term that we learned at some point during this year. I'm going to say a net force, because this is a little bit more precise way of saying it. So if an object experiences a net force that is not zero, then its velocity will change. So here's an example of a game of tug-of-war. And so let's say we got this big guy over here on the left. He's going to be pulling to the left. And this vector represents the force that he's applying to that rope. Well, let's say we have a little guy over here on the right side. You can see that his vector is much smaller. Now, these two forces are unbalanced. The left one is obviously bigger than the right one. Now we can represent the fact that the left force is bigger than the right force by talking about something called the net force, or the sum of forces. So let me just take a screenshot of what we have over here. So we have a vector pointing to the left, and we have another vector pointing to the right. And you can see that the force pointing to the right kind of cancels out some, but not all, of the force pointing to the left. That means that the sum of those two forces, or if you add the two forces together, then you get this net force in blue. So that is the net force. It's just what you get when you add all the forces together. If the net force points to the left, guess which way this, what is this? Looks like a coal mine crate full of candies. You know, one of those coal mine car, not a coal mine crate. Now, obviously this guy's bigger. He's got a bigger force. All these candies are going to go in his direction. See? Oh, try as he might, the little red man isn't going to get any candy. See? Blue wins. Now, let's return these guys. What if I made the right force bigger? What if I put another guy over here. Ooh, look at that. The sum of the forces is 0. The net force is 0, which means the forces are balanced. So let's see what happens. Who's going to win this time? Is it moving? No, it's not moving. The forces are balanced, so the coal mine car full of candy, its velocity doesn't change. Its velocity started at 0, and it stays 0 because the forces are balanced. Now here's another example of forces at work. We've got a little man over here, and he's going to be pushing this file cabinet. Now I want you to pay close attention to what's happening over here, because this is a live force diagram. Now, this force diagram is for the file cabinet. You can see that the force of gravity is in purple, pointing down. And then this Fn, it stands for normal force. There's really nothing normal about it, but it is the same exact thing as what we call the support force. Okay? So whenever you see an F and a little n, that just means normal force, which means the same exact thing as what we have been calling the support force. Support force makes a lot more sense to me. Now, watch what happens when we take this file cabinet and our little man tries to push on it. You can see that he's applying a force in blue over to the right, but there's a force that is opposing the applied force. Now, the file cabinet isn't moving. That means that the friction force that is opposing his applied force is the force of static friction. But if the applied force gets big enough, watch what happens. And watch the force diagram at the top right as well. It's getting bigger and bigger and bigger. Oh, look at that. The file cabinet starts to move. And also notice that we have a total force, which is just another way to say the net force. The total force is what causes the file cabinet to move. Oh my goodness. Someone took my file cabinet. Now, if we push the file cabinet to the left, notice that the net force, the total force, also points to the left after we apply enough force. And then if I let go, look at that. There's no longer any applied force, so the net force is equal to the friction. And in that case, that was kinetic friction, because the file cabinet was moving, and whenever an object is moving, it will experience kinetic friction. So now we are applying a force. The net force is causing the file cabinet to speed up, and then all of a sudden, when I let go, the net force slows the file cabinet down. So let's summarize what we've learned so far. Newton's second law of motion says that a net force causes an object's velocity to change. And in the example that we just saw, the net force was causing the speed to change. Okay, it wasn't causing the direction to change. So now let's choose something else. How about a sleepy dog? We're going to push this sleepy dog. So I'm going to apply force. Ooh, look at that. It didn't take much applied force at all to get the sleepy dog to move. Notice that the sleepy dog is moving a lot faster than the file cabinet was. In fact, the sleepy dog is still moving, and it's still going, and it's going, and it's going, and it's going. And I don't know if it's ever going to stop. Oh my. Now notice that it's much easier to get the sleepy dog to move. It's much easier to change its velocity. Now why is that? Well, first of all, it's much easier to get a large net force acting on the sleepy dog. But also, notice these numbers over here. The sleepy dog has a mass of 25 kilograms. The file cabinet had a mass of 200 kilograms. So the file cabinet has much more mass than that dog does, even though this dog it appears to be gigantic. But I think that's just because this is a simulation. So a net force causes an object's velocity to change, and a bigger net force causes a greater change in velocity. And I hope that you recall that a change in velocity over a change in time is an acceleration. So a net force causes an object to accelerate. A bigger net force causes a bigger acceleration. That makes sense, right? If you push on an object harder so that it experiences a larger net force, then its velocity will change faster, which means it has a bigger acceleration. But as we saw with the file cabinet and the sleepy dog, mass, an object's mass, resists acceleration. And that means that a bigger mass will cause or will allow for a smaller acceleration. Okay? Now, Newton's second law of motion can be summed up quite nicely in an equation. And this equation will tell us what the acceleration of an object is. So, if a net force causes an object to accelerate, and a bigger net force causes a bigger acceleration, here's our force, but mass, the mass of an object will resist the object's acceleration, which means that we're going to be dividing by the mass. And this is Newton's second law as an equation. The acceleration that an object experiences is equal to the force, and in particular, I need to be very careful about this, the net force. The acceleration that an object experiences is equal to the net force acting on the object divided by the object's mass. Now, as we've already said, forces can be represented by vectors. And acceleration, as we also saw, can also be represented by a vector. This means this equation not only tells us the size of the acceleration that an object experiences, we just plug numbers in for the net force and a number in for the mass, but this also tells us the direction of the acceleration. And that's going to become much more important when an object has more ways that it can move. Instead of just left and right like the sleepy dog, if an object can move in 2 dimensions, or in the real world in 3 dimensions, then this equation becomes much more powerful and useful. So let's bring back our little red ball. As we already said, this green arrow represents the velocity vector of the ball, but we can also look at the acceleration of the ball. And Newton's second law, this equation form, says that the acceleration points in the same direction as the net force. Oops, that's a sleepy dog again. So this blue arrow represents the acceleration, but the blue arrow also represents the direction of the net force. So the acceleration and the net force point in the same direction. So you can kind of see that if the blue vector is the force that is causing that red ball to move, when the blue arrow is bigger, it experiences a larger net force, which means it's accelerating at a greater rate. So this ball is moving to the left and to the right, just like our sleepy dog was. But what happens if we make this red ball go in a circle? What direction is the force going to point? Well, let's see. Look at that. The force is pointing toward kind of the center of a circle, somewhere over in here. Now, the green arrow, again, is the velocity of that red ball. And when the velocity vector is at a right angle to the acceleration vector, which is in the same direction as the net force, this causes the object to change its direction, but it's not changing its speed. Okay, now let's take a look at some real problems with some numbers so that we can kind of get an idea of how Newton's second law as an equation really works. So Sophia, whose mass is 52 kilograms, experienced a net force of 1,800 newtons at the bottom of a roller coaster loop during her school's physics field trip to the local amusement park. Determine Sophia's acceleration at this location. Well, we know the mass, 52 kilograms, and we know the net force that she experiences at the bottom of the roller coaster. So it's going to be very easy just to plug these numbers into this equation. Now, I have been kind of babying you a little bit in the sense that I am making it very easy to work with the units in problems like this. So just as an aside over here, a little thought bubble. When your net force is in newtons and you're dividing that net force by a mass that's in kilograms, then your acceleration is going to come out as meters per second per second. So in this problem, we won't have to worry about our units. We won't have to convert anything or do any heavy thinking there. Okay? So now let's go ahead and calculate this. 1800 divided by 52 equals, oh, it's a wonderful fraction. So I'm going to convert that to decimal, 34.6. So the acceleration that Sophie has at the bottom of this loop in the roller coaster ride is 34.6 meters per second per second. That is actually quite a significant acceleration. Hopefully, as you do these problems, you will get a better idea of what is a big acceleration, small acceleration, what's a big net force, small net force, and so on. So this was a very simple problem. Let's look at a slightly more challenging one. I'm going to go back here and I'm going to copy and paste Newton's second law in equation form. So Captain John Stapp of the U.S. Air Force tested the human limits of acceleration by riding on a rocket sled of his own design. His rocket sled, known as the Gee-Whiz, had a mass of about 82 kilograms. What net force would be required to accelerate the Gee-Whiz and Mr. Stapp, Captain Stapp, at 450 meters per second per second? Actually, now that I'm looking at this problem, which I found online, it doesn't give us enough information. It doesn't tell us what the mass of the Gee-Whiz is itself. Actually, this is kind of an annoying problem because apparently Captain Stapp and his rocket sled both have a mass of 82 kilograms. That's what I'm getting from this problem. Okay, well, so that means that the total mass of Captain Stapp and his sled is 82 plus 82 kilograms, which is 164. Okay, so that is the total mass that we are dealing with here. So let's go ahead and plug these numbers into Newton's second law. So the acceleration is going to be 450 meters per second. So 450 equals, now the mass is 164 kilograms. This is, again, the mass of Captain Stapp plus his rocket sled. And we are trying to find the net force. Now, in order to solve this equation for the net force, we're going to have to multiply both sides by 164 kilograms. So these cancel out. And so the net force is simply 164 times 450. 164 times 450. So about 73,800. 73,800. And the units of this net force are newtons. Okay, so that problem wasn't too bad either. Now let's look at a final problem. Here we are given a force diagram over here. Ethan is dragging a bag of grass from the garage to the street on the evening before garbage pickup day. A diagram at the right is a free body diagram. And let me just translate this for you. By free body, that's the same exact thing as saying a force diagram. I have no idea why they call it free body. It's such a ridiculous name. And this diagram uses arrows to represent the forces acting upon the bag. We know that. Each force is labeled according to type. Yes, so we have friction force.
It's 12 o'clock.
It's 12 o'clock, thank you. The applied force, force of gravity, which is the same thing as weight. We know that. And then the force pointing upward is the normal force, which again, we call that the support force. Okay, so I'm just kind of translating this for you using terminology that makes sense to me, at least. Now, the magnitude of the force is represented by the size of the arrow. Yeah, we already know that. Come on, give us something challenging. Let's use the force diagram to determine the net force acting on the bag. Now we're given numbers that represent the size of these forces. So the normal force is pointing upwards, and that has a value of 60.5 newtons. And gravity points downward, but it has the same exact magnitude as the support force, which means that the net force is only able to point left or right. Okay? It can't have any upward or any downward part to it, because the support force and the weight cancel each other out. Now we are also told that the applied force is 40.2 newtons. And then the force of friction, which opposes the direction of motion, which in this case is the direction that Ethan is pulling the bag of grass, the force of friction is much, much smaller. It is only 5.7 newtons. So we want to find the net force. Now we know that the net force is not going to go up or down at all, because the support force is balanced by the weight. But the net force is going to point a little bit to the right. And we know that because the applied force is bigger than the force of friction. So the force of friction is kind of taking away some of the bite of the applied force, because they point in opposite directions. What we're going to have to do is we're going to have to take the applied force, 40.2 newtons, and we're going to have to subtract the force of friction. So 40.2 minus 5.7 is 34.5. And this, ladies and gentlemen, is the net force, 34.5 newtons. Now I want to add some complexity to this problem. First of all, I want to find what the mass of this object is, of this bag of grass. How in the world are we going to find the mass? Well, actually, we have enough information to find out what the mass of this bag of grass is. Because we know that the weight, the force of gravity on the bag of grass, is 60.5 newtons. So let me just write that out down here. If the weight of the bag of grass is 60.5 newtons, I hope that you remember this formula. Weight is equal to mass times g. Now g is that very special number, 9.8. Okay, this is the acceleration due to gravity. And when you multiply that by the mass of the object, of any object, you're going to get the weight. Actually, this g is only for Earth, of course. You know that. So that means that we can find the mass of this bag of grass very easily. We just stick in what the weight is, 60.5. Leave the mass alone for right now, but then the mass is going to be multiplying 9.8. Okay, and now we have an equation that we can easily solve for the mass. We just simply have to divide both sides by 9.8. So this means that the mass of the bag of grass is 60.5 divided by 9.8 is about 6.2. I'm going to round it. 6.2 kilograms. So if that is the mass, and this is the net force, let me just spell that out. And this is the mass, which we just found. That means that we can find what the acceleration of this bag of grass is, because we have the net force and we have the mass. Now recall that Newton's second law says that the acceleration of an object is equal to the net force divided by the mass. So this is a very easy calculation that we can do. The acceleration of that bag of grass is 34.5 divided by the mass, which is 6.2. So the acceleration is 34.5 divided by 6.2, let's round that, 5.6. And the units are going to be meters per second per second. Now, to be honest with you, this is actually a very ridiculous problem, because this is a very large acceleration, and I don't think anyone can make a bag of grass accelerate that much by dragging it, at least maybe for a short period of time. But the idea is still there, that we can solve a problem like this and find actually a lot of different information. So that is it for this video. And again, remember that the key idea that I wanted to get across in this video is Newton's second law of motion can be represented by this formula right here.